All right, so this is our um, recording for homework two.
I'll be starting us off with problem one. And let me share my screen real quick. Okay, so problem one, we have a rectangular plate at the bottom here, and then there's a pivot point at the top. The origin point is at right below at A. So the weight of the plate itself is going downwards into the page, as you can see here, from point O instead. It's not from point A. But you could possibly draw it from point A. And we have point B, point C, and point D, which is R, um, pointing toward point A because it's supporting the weight of the plate itself. So it's pointing toward point A to support what the weight is down here. And that's how I kind of drew the free body diagrams. And that's about it. Any question?
Um,
Um,
you said something about like how you put the weight on a how does it work?
So when you draw a free body diagram, because it's on the same axis, when you move it upward, doesn't actually matter. Like logically, it's just moving the way itself upwards, whereas it doesn't really actually matter all that much, to be honest. In a 3D, in three spaces, it's a lot easier to see that it's on point O, but because they share the same unit vectors, like it's just the direction itself is the same direction, so it doesn't matter if you move it up to point A or point O. So it still have the same unit vector.
Hmm.
Yeah.
anyway, um,
So now we'll be going to the next part of this problem. Let me share my screen.
Okay.
your screen.
Yeah.
Okay, so up here I have the diagram very nicely drawn with all the different forces that are acting on the system. And so start out with how you started with the unit vectors. So with the unit vector tension in B to A is equal to like the magnitude and the unit vector basically. And so to find that unit vector, you need to basically um, divide the actual unit vector by its own magnitude. So in the case of tension from B to A, um, it goes to the right 320 meters, goes upwards 480 meters, and it goes into the page 360 meters. And in order to find the magnitude, you just take the square, add the squares of each of them, and then take the square of the whole thing. And then you would, in order to like get like the unit vector in terms of like IJK, it's you don't have to add the top 320, 40, 360 into one singular number. Instead, you have to divide each of these individual numbers by the whole magnitude, which would result you in this vector. And then you repeat the same process for the rest of them, and then you get the resulting vectors for each piece of tension. And now you also have to consider the weight. Actually, no, scratch that. Um, you use the now we can now add the all of these vectors into basically one equation in which all of the vectors equal zero, which is stated here. And we also have to include the weight, which is in only acting on only one direction, which is the j direction. And so if you kind of sort everything around, add up all the I components, add up all the J components, add up all the K components, you get this nice system of equations where you have two two unknowns and this third one right here. This one is known. So you can easily basically rearrange the whole problem in order to get these values down here. And then from there, you can solve for the weight by taking the J unit vectors, which is 0.7, 0.64, 0.729, and multiply them by your given tension values. And then from there, you get the weights.
So you ended up like just solving the systems of equations like traditionally?
Yeah.
Oh, okay. Because I mean, for mine, I just put it into a matrix.
So this one's easy enough.
Yeah, I guess.
Anything else?
Mm,
No, that's not.
Okay, and I will be going. Oh my God, I will be going over the last problem. Can you guys hear me? Okay.
Yeah.
Okay. All right. Um. Okay. So this is the problem that I'll be doing on the icy surface. So in this problem there are four different forces involved, which I put into the free body diagram. And so you have the tension from both of the ropes that this guy is holding on to. And then we're also given the only given quantity is his weight, which for me was 170 pounds. And then there's also an additional normal force from the surface, which is perpendicular to the surface. And so I decided so first I wrote down all the coordinates to make later calculations easier for all of the points. And then I attempted to find out the normal force first. So I did this by there's like a laser feature. No, I don't think so. Doesn't matter. So I found the I and J components of the normal force by just using the what's it called? The unit vectors method, which is just the I component or the X component is just cosine of theta. And the Y component is sine of theta. And I chose you can see the angle that I chose for theta. Um, and then yeah, I just put that in the formula. So I got that for the normal vector, um, which is right here. And then for the tension of AB and the tension of AC, I did the same thing as you would do in problem two. So I also just put all of these points into the unit vector formulas. And this is what I got for all the coordinates. And we're also given the weight as negative 170, or it's negative because I designated this coordinate system, so it goes only in the negative y direction. And after that, I summed up all the forces in all of the different directions, which should all equal 0. And then I converted that to matrix, which you can see here. And then I put it into matrix calculator, and it spit out these values. So I could have solved it by hand, just not using matrix, but it is easier this way. And I think they told us we could use matrix calculators. So yeah, that's how I got these answers. All right. Any questions?
No, I think it's really good.
No.
All right. Good.